Welcome everybody to day 3. This is the last day. We have another exciting morning with a review of yesterday's speakers, and then there will be a tour in the afternoon. So the first part of the morning would be a recap of what was discussed in the breakout rooms yesterday. So I would invite on stage Avinaya and I think it was Carlos.
Hi everyone, good morning. Well, I'm going to do a recap of the breakout session that we had yesterday on quantum algorithms for differential equations. First, I would like to thank my co-lead Ruben and Anarita for taking the notes. Thank you both. And thank you to all the participants. We had like really good discussion, and I'm very happy to say that like everyone had a chance to speak and voice their thoughts, and it was a really good discussion. I'm going to do a brief overview. So kind of some of the things that we first discussed was like what differential equations would be of interest to the climate and weather modeling community, kind of having the goal being to compile such a list that can be used jointly across both the quantum computing community and the climate modeling community, that we can use as a shared basis for testing and development. And some of the things that we discussed, maybe we can start with simple ODE systems like Lorentz 63 and move to Lorentz 96, and then to move to partial differential equations, and then kind of add in all the complexities of a geophysical fluid dynamic simulation. And there was some, agreement with the participants that it's like, it would be good to like distinguish what algorithms are better suited for the noisy intermediate scale quantum computers versus more future fault tolerant algorithms, kind of compiling a list like that and sharing it with the kind of the climate modeling community would be helpful for researchers. And there was some interest in kind of having small working groups to kind of continue after the workshop, with the goal being we can kind of more concretely like work on some of the topics that we discussed, maybe write a research paper, maybe write a review paper as part of this. And like compiled a wish list of some of the problems that can be of interest, like Navier-Stokes, Lattice-Boltzmann, doing parameterization, cloud microphysics, radiative transfer, looking at Liouville and Fokker-Planck equations being some of them. First half of the session. In the next part, we had a discussion on some of the quantum algorithms that people are working on today, and what we can learn from them. What we like, as we went around the room, every participant shared kind of the algorithms that they had expertise working in for the applications that are of interest to them, and they shared a little bit on like what worked for them and what did not work for them, and to kind of compile a list that I'm going to talk about next. And I thought this discussion was super valuable. It really draws from everyone's expertise and their experience and like doing some hands-on work with many of these algorithms. One thing we discussed first was that it's likely that there is no like one algorithm that's going to be best suited for like any kind of PDE or ODE that you want to solve. Algorithms really should be tailored to specific PDEs and like kind of the underlying physics and the structure of them, and to be benchmarked against the best classical methods for that equation, so we can really see a good apples to apples comparison between the quantum algorithms and classical algorithms. And there was some talk on variational algorithms. I mean, that maybe they're like not really great. Ansatz selection is kind of trial and error, and how you do the prepare, measure, and reload cycles, it can really be a bottleneck. But there was some like encouraging news from some participants who shared that like there can still be potential in using variational algorithms, like especially if you like kind of take the parameters that were learned out of like your ansatz and use that somehow after that to like in a classical post-processing cycle to directly kind of learn the state and work more on the state. So there is still like more work to be done there. Talked about tensor networks, how these are really powerful tool, a powerful quantum inspired tool that can be used both for like loading your states as like an tensor network state, or even as a tool for just doing quantum inspired algorithm development. Explored some ideas on spectral methods and doing optimal linear embedding to kind of replace the finite grid discretization approaches that are taken commonly. Another thing we discussed was like how the feedback loops must stay low dimensional, or kind of the readout and the reloading cycles would dominate. And so it's really important to keep this as low as possible. And we all agreed that nonlinearity is still the hard part. Like we don't really have a good solution currently. We know we have a lot of different techniques that people are working on, but there is as far as I know, there is not one solution that really is the best solution. So it's still really hard and challenging, and it's something that we need to really think about and solve. And we only spent a little bit of time at the end, kind of discussing this timeline of when we can see, hope to get some quantum advantage for differential equations on hardware. We agreed that kind of near-term research on NISQ hardware versus doing fully fault-tolerant simulations are very different, and the timelines for maybe getting advantage for solving linear PDEs can be closer than kind of doing fully nonlinear PDEs, and long-term integrations with hardware need error correction.
Oh, good morning. So my name is Carlos. So yesterday we mostly tried to answer some of the 4 key questions that were given to us. And in part, a lot of the questions went around trying to identify sort of trade-offs between high fidelity problem representation and the need for dimensionality reduction. In particular, something that came up is the idea that some problems, if you do reduce the dimension, they might become classically tractable. So that's maybe something that you want to kind of keep in mind, that in an effort to try to make a problem more or amenable for quantum and for a specific technique, you might be reducing it to such a degree that then now you don't necessarily need the quantum computer anymore. So that was kind of a theme that came up out of this first question. And it's something worth keeping in mind. So that was a central worry. Another thing that came up was the fact that NISQ hardware leaves almost no room for trade-offs between circuit depth and problem size because these are so restricted devices. So you have to be careful about when actually constructing metrics to evaluate the devices that we're talking about, because we're already at the very stringent space, right? There's not a lot of room to play between a lot of variables. So another comment that came up. And on top of all this, for a lot of optimization problems, there's a big sort of elephant in the room that has emerged over the last, there's a huge literature has emerged over the last 5 to 10 years, the barren plateau phenomena, which basically means that for a lot of the Hamiltonians of interest that are evaluated against linear objective functions, so think about an expectation value, and you're then optimizing parameters for these Hamiltonians, they have decaying gradients or exponentially decaying gradients with system sizes. So for small sizes, a lot of the results might look nice because they're small, but then we know that at scale, effectively, these gradients decay. A simple picture that I like to think about this is that this is basically somewhat rephrasing the cursive dimensionality, but for gradients. So effectively in higher dimensions, when you're evaluating a linear objective function like an inner product, your vectors are going to become really, really close to each other because your dimensions are so high. So this also happens for the gradients, and that just translates to gradients being really, really small, right? So it's maybe kind of giving you some intuition there. However, a discussion emerged on this topic. Over here, we're in sync. No, we're still here. So strong consensus emerged that the issue is not necessarily just you parameterizing a circuit. The issue is in the variational loop, right? The idea that you have to compute gradients and then do a loop, where you're going to start experiencing issues. This is a mathematical issue. It's not just some engineering issue that we need to bypass. It's not an issue with us getting better hardware. It's just mathematically this fact of vectors getting kind of close to each other in high dimensions for linear objective functions is something that it's going to be hard to bypass. So there are other nuance that came around with this discussion, some dissenting maybe nuances. So barren plateaus do assume sort of random onsets. So basically these statements are about kind of concentration of measure. So there could be some really specific problems in variational circuits that you could still solve with a loop if you can identify a specific Hamiltonian and a specific initial condition, right? So it's almost like the onus is on the application people to find this sort of Hamiltonian, but we do have strong statements that it's unlikely. And then this also does not rule out the possibility of sort of polynomial advantage. So there could be still some polynomial advantage in this sort of variational loop. So that's something important that was brought up. Another important point was that maybe variational circuits are useful for teaching, right? So like this is, people are familiar with gradients, people are familiar with sort of gradient descent. So maybe this would be a way of getting some of the folks that are more familiar with that into quantum as a teaching tool. And then there are other topics, like for example, quantum control, where people have actually optimized parameters and things of that nature. So yeah, so the key thing is like the classical feedback loop, not necessarily the parameterized circuit itself. That's kind of where the speed up died. Alternative methods to variational circuits for optimization that I think are now starting to emerge are sort of more end-to-end Hamiltonian evolution with no mid sort of measurement in your computation. So I'll point out some work by Nathan Weeb's group out of University of Toronto that they've actually started looking at ways of embedding these optimization problems into sort of a desired Hamiltonian that they can evolve. And this gives you a way of then reading off the solution at the end with some guarantees. Yeah, so that's something that kind of came up there. You maybe move to show some other points here while I kind of summarize some of them. So a question that came up that I thought was sort of interesting is that there was this question of, okay, so we're looking at near-term devices. How do we define near-term devices against, let's say, maybe fault-tolerant devices or devices like that, or more future-term devices? And it's kind of hard to get an idea of when we're going to have this transition point. One thing that was brought up is the thing that instead of necessarily thinking about a specific timeline, let's say like 2030, this is where we're going to call like fault tolerant devices. I think it's maybe worth keeping an eye out for like when we transition from like physical computation to logical computation, like basically something like having like, okay, we can do a logical qubit and we kind of know that, like Google show that we can perform logical operations, and as you increase the code distance, your error goes down. But right now that error hasn't gone below the physical error, right? So we're still kind of at this point where like logical operations might not be hitting the physical or crossing the physical threshold. That could be a way of measuring a milestone. And then the next milestone might be, can we perform gates, and in particular entangling gates across logical qubits, right? That moves us, across a boundary area there. D-Wave was brought up as far as optimization. So a thing that was brought up when it comes to D-Wave is the fact that D-Wave devices, they've published a couple of papers where instead of claiming a quantum advantage, they're now claiming more of a cost advantage, where like instead of having to solve a really hard optimization problem across like a distributed HPC system, you can just use the D-Wave chip to solve something similar and get reasonable solutions out of it. So that could be also a claim that when we're talking about advantage, we should keep in mind that maybe not necessarily exponential advantage or computational advantage is the only advantage, right? There could be an advantage in cost, energy, etc. So something that was worth pointing out. So a significant gap that was identified is that maybe something worth thinking about for maybe a future workshop. A lot of climate problems so far in optimization, I think folks have been thinking about operational problems, but maybe some problems that are worth solving in atmospheric science are more related to the chemistry of the atmosphere, right? And like more of the nuance problems, like for example, quantum chemistry and flavor. And these, we know quantum computers can help here. Something worth keeping in mind. Regarding the tooling, so maybe I'll move to the next one. So I think that was, yeah. So here we go. Regarding the tooling, there wasn't a clear consensus as far as like what set of tools are absolutely necessary to translate to QUVO devices, let's say. There was strong consensus is on the need for a set of benchmark problems. And since we're kind of discussing climate applications, what benchmark problems in climate science are worth us thinking about when we're developing, let's say, quantum algorithms, and in particular, optimization quantum algorithms. So this was definitely something that emerged as a strong need as far as tooling. It's more like, can quantum and domain people sit down and identify where are these problems that are at the boundary? And the financial community, the quantum financial community, if that's a word that can be used, have actually dealt with a lot of optimization problems, and the financial systems do behave somewhat similar, I guess, in some senses to climate systems. So something that was brought up was the fact that you could maybe try to merge these two communities somewhat in the future to try to identify what tools have they already looked at that haven't quite worked for optimization that can maybe be ported over to like the climate problems that we face. So that was, I think, an interesting potential future merger. And a lot of these folks, at least the ones that work in quantum, are fairly open as far as sharing a lot of their results, and they publish actively, particularly JP Morgan Group, and it was one that was brought up. So I think I'll probably leave it there. So any questions?
You mentioned something about the adaptive grid for hurricane modeling and stuff. So what kind of adaptive modeling grid are we talking about? Is it like, I don't know if you are familiar with the MPAS's refined mesh concept. So in a way, you have a global, let's say 15 kilometer everywhere, and then you have a target area, let's say a hurricane over North Atlantic.
Mm-hmm.
We have like specifically targeted 3 kilometer or 1 kilometer for that. So that way you have a global continuous field of 15 kilometer meshes that are hexagonal. And then you have your target area that is refined. So currently MPAS supports multiple refined meshes. Let's say we have 5 hurricanes over different, one in Indian Ocean, one in North Pacific, like East Pacific, West Pacific, and stuff like that. So yeah, just a clarifying question, like what did you mean by the like adaptive mesh?
Yeah, so to clarify the context of that note, the discussion, so the suggestion was that choosing an optimal mesh is a optimization problem in itself. So some of these techniques could be applied towards finding optimal meshes.
Hi, Ruben Immersion. Thank you both for the summaries. Okay, so this is going to be kind of very general, but regarding variational algorithms, suppose you have some kind of warm starting procedure. How does that help you circumvent barren plateau issue? Do you expect, I'll just say a good warm start, whatever that means. Do you expect that to help totally avoid barren plateau? Is there more to it than that? What are your thoughts on it?
So the issue with showing that like the technique is never going to work is that the mathematical tools for that would be very stringent, and it's actually you can't kind of prove it because in some smaller cases it does work, right? So it's not that it doesn't work in general. The argument that has emerged in the community is that for large sizes, for fairly large sizes, and for circuits that are expressive enough, so that also translates to some degree to kind of circuit depth. What we know is that what the landscape goes from being kind of like, you know, more convex to being very, very, very peaked. And then there's some results by Marco Cereso and other folks that they've translated this peakness and expectation to actually the landscape having a really what they call narrow gorge, which just looks like, I mean, it's kind of hard to draw a picture, but it's imagine like a bowl that just keeps getting closer and closer, and you just have a really small hole. So you have to be, the issue with warm start is that what that means is you have to have a good enough answer. Yeah. But as the gorge gets smaller, good enough answer is the answer, if that makes sense. So like meaning if you have a good enough answer, like you're already at the region where like you're already decaying really, really fast in the landscape. Again, the tricky about the discussion is that it's right now we have a lot of evidence that in general this is not going to work, but then the onus now is on the domain experts to find a specific Hamiltonian and a specific warm start technique that could make it work. But that's more, I think the shift is more changing from this is going to work, we are certain that this is going to work, to like, okay, now you have to show us a problem application and a warm start. Well, it will work because we don't see evidence that it will in general. So that's kind of my take on this. Again, there are some nuances. When it comes to barren plateaus, the optimization problems are specific to when you're evaluating expectation values, right? There's work that if you evaluate, let's say like a divergence instead, there are no barren plateaus, and you can show that there are no barren plateaus. So maybe I think the shift in the future would be to switch to other, type of techniques that we know that have more, leeway. But the problem with linear expectation values is the issue that the curse of dimensionality is roughly the argument that really applies here, is that your vectors just get really, really close to each other. And we need, for quantum in particular, we need to solve problems that are at scale, right?
Yeah.
And yeah. So does that answer the question?
Yeah, it's really helpful. Actually, I do have some other ideas I'll just take offline with you.
Sure, yeah.
I've done a little bit of work on it. I'll just say I am too skeptical, but I feel like the PDE community, we might have some ways to circumvent this and
Okay.
good warm starting
Great,
features that I'd love to share with you.
Oh, absolutely. I'd love to talk to you about that. Yeah, that'll be
Thank
awesome.
you.
Yeah, thank you.
Hi. So, past 2 days, we talked about both quantum sensing and quantum computing. From your perspective, if we were, from the quantum sensing community is concerned, if we were to generate, data products or entangling our sensors with the quantum computers, what type of data structures are ideal for ingesting directly into the quantum computer?
Right.
Also, as a hardware, in terms of, is there a way we could directly link between the sensors and the quantum computers? And what would that architecture be like?
Yeah. Actually, I really like that question because, it's a question I'm sort of passionate about, and the fact that, so far we've been thinking about sort of BQ, EQ, AOA more from, you have a Hamiltonian, you're kind of optimizing parameters in a classical loop. The story of learning from quantum data directly is completely different. That story is actually really rich, and like there's belief that there's a lot of advantages there. In part because you no longer have to worry about the input bottleneck, right? So imagine that you have an array of sensors capturing actual quantum states. You can then potentially train a variational circuit that more in sort of a generative way, where let's say you have a bunch of circuits that you want to be able to like reproduce on the fly later on. You can train a surrogate model that can then spit out these circuits that you've learned from the sensor. Now, obviously, you can't clone them, so you'll never be able to learn them perfectly, but there's nothing that violates the rules of quantum mechanics when it comes to approximation. So you can learn a surrogate model to then learn from this sensing data, so to speak. An example of this, I've done a little bit of work on this where, let's say you take computing the ground state, the actual ground state of a molecular Hamiltonian is expensive. So you could, but instead what you could do is you can maybe, with a high accurate quantum computer, you can maybe sample certain ground states and then interpolate the landscape with some surrogate model that comes from quantum machine learning. So in the work that we did, this actually worked really well. You don't need that many sample points to be able to interpolate the entire landscape. So I can see a lot of problems in sensing where you maybe want to measure a lot of different instances, but you want to like sparsely sample some of the instances, and then you can use a quantum machine learning model to use as a surrogate to sort of interpolate across your landscape. So that would be an application where sensing and quantum machine learning techniques can be put into place. And add another example of something that's end-to-end, right? Here we're not necessarily having to input a lot of stuff from a classical perspective other than maybe the controls and things like that. So I hope that answers the question. Yeah.
Any other question for Carlos? If not, thank you, Carlos. Thank you, Abenaya. So the next session would be quantum computing and sensing for extreme weather events. In the last couple of days, you have seen exploration how quantum computing sensing can bring benefit to climate and weather. We thought we would be good to zoom in a little bit in something more specific related to extreme event. Things about hurricanes, flood, wildfire. Our next speaker is Dr. Peña. Please come to the stage. So I would like to introduce the speaker. He's a professor from the University of Connecticut and specializes in meteorology and environmental modeling. He graduated from the University of Maryland and is an expert in weather forecasting for power grid resilience. He's also a contributor to Eversource Energy Center and the Quantum Connecticut initiative.
Okay, thank you so much for inviting me for this as an oral talk. I added a couple of slides just to show my kind of my passion and how this evolved into this concept that I'm trying to address. So the topic is about the idea of using quantum scan, which it's very efficient as a replacement of our current strategy in numerical weather prediction, which, as you know, we truncate essentially our models. And even when you have convective allowed models, we still only model the convection, but not the microphysics. So we always end up with parameterizing. So I'm trying to address this from a different perspective. I'm not claiming any quantum advantage. I'm just showing a method that I'm testing, and I'm always welcome to, of course, contribute or to work in collaboration. So the passion I'm about. So I work for the National Weather Service for 15 years, developing models, especially global models and climate models. One of them is the Climate Forecast System version 2 and the GEFS model. And one of the issues we had is the errors. So errors start, let's say you have a pattern, initial pattern, which would be a stream flow, and then it tends to get the, let's suppose that you have a twin experiment. One is the truth, the other is the forecast. So there is an inflection point, and with times going forward, it gets saturated. So that's a very important part because we already have some sort of analytical procedure to have this structural alignment. And we use that as a deformation gradient called Jacobian. So, but the nice thing also is that during the early growth of the error, the multidimensional space is actually can be compacted into a smaller space. So, and I'm going to show you what the magic or what I'm passionate about. During the early stages after the initial condition, by the way, numerical weather prediction is an initial value problem, essentially. Initial errors start to grow exponentially, and they are dominated by Lyapunov vectors or nonlinear Lyapunov vectors, depending on the conditions of the system. So here I plotted the associated phase space geometry of the attractor, and then I defined Lyapunovs that are leading Lyapunovs, which I put like parallels, and then trailing Lyapunovs, which could be perpendicular. So they start to grow at the end, but the nice thing is that when you combine the two, they are like clocks that tell you at what phase in your lead time or your logistic curve you are going. And this is important because most of the generative AI actually do not take this into account. And so they tend to generate too much, I would say, hallucinations. The other thing is that one could demonstrate that it's possible to decompose the errors into these Lyapunov or in this case saturation regimes, and using this beautiful mathematical logic equation. Here on the panel on the left is the typical errors of 3 waves, let's say. And when you do the transformation, this logic function, they get linearized. And the slope of these lines are the Lyapunov vectors that I'm talking about. So when you have a multi-scale system, some of the Lyapunov vectors tend to grow much faster, so the slope is larger. So how about if we use, instead of using our regular compact methods, we use a logit space. So each of these L lambdas would be an axis. So now you have a space that is very compressed. So you can now really get the essence of what really matters, which is how the error grows. And so in that space, if you use Koopman operators, then all your observables would be linear. And that's a very nice feature because then we can translate that or mirror that into a quantum system. So going about now to our talk. So just to give you the introduction on my background and what I'm passionate about. And now I'm going to talk about the problem I'm presenting in today's talk. So the main point here I want to address is the problem that convective trigger, not convection, but the convection trigger, it's a microphysical and also involves mesoscale and also involves large scale. So it's initiates at subgrid scales. And when you don't have it in your models, if you don't represent those in your models, then it contaminates. It creates forecasts, errors that grow, and then contaminate and upscale to other scales until then you get this saturated error, worthless forecast, and you don't use those anymore. And for 7 decades, we have actually address the problem of errors by bias correction, stochastic parameterizations, and noise filtering. We do after the fact error corrections, which do not work actually, because as you know, the phase space in which the trajectories move, it's a chaotic system. That means they never repeat. So we have to all the time start bias correcting again and updating the bias correction and do parameterization and all those things. This is something that quantum computing, I believe, should be able to address, because at the bottom of this problem is that the convection trigger, it's a many-body problem. And I'm highlighting here the many-body problem. Why? Because it belongs to this type of phenomena or emergence that comes from microphysics, boundary layer memory, turbulent entrainment, and all those processes that somehow they combine together and give rise to let's say deep convection or transition from shallow to deep convection. The other thing is that a problem that it's these activation mechanisms are threshold, so you cannot average them. You cannot quickly get an easy representation. You have to treat them individually as a many-body problem. So I think there are tools in quantum computing. I'm not familiar much. I'm not an expert on quantum computing, and that's why I'm happy to present in this forum. I just want to put some of the ideas that I believe it could be helpful on preparing a plan for attack on this problem that I just presented. So let's start with the physical premise, so that the convective onset is a critical transition, like it has a behavior, and we can create a criticality coordinate, which some research has demonstrated that it's one of the driving observables is the column of water vapor. So you have that, and then, but this trigger happens in this small range. One could, there here, by creating this coordinate, one could actually create a decision-sensitive band, like this shaded area. And then the other thing is that our task would be to understand where or identify where this is happening in the entire globe or in the domain of interest. So this is kind of a quantum search on when these bands are happening. The study it's divided into three connected thrusts. One is the criticality aware inference, where we define what is the probability score. And then the second, which is the one that I'm emphasizing here, is the quantum critical set inference, or the SCAN, I call it. And finally, the trust number 3 is the how to recover, how to re-enter into the physical system. So as you can see, I'm going to show that we do not plan to run the model into the quantum computer, but we would like to have only the inference or generate the inferences into this computer and then reuse that on the HPC, on the classical supercomputers. So trust 1 and trust 3 are classical and will remain classical on every outcome. So defining the local criticality, it's generic for now, and we create this function S, which is the product of the posterior probability of these supercritical given observations in this narrow range R, and then multiplied by the expected observational gain, and lambda, it's called the anticipated error growth. There are some equations or analytical equations that are provided later, but essentially one could define this criticality score. Next is the operational question. So suppose that we have the capability in our supercomputer or in our system, in our quantum computing, one could identify or refine regions which maximize the forecast value. Forecast value is here, it's the V, the expectation of this forecast value. So our task is to use this quantum scan to identify these boxes into or domains, small domains, and perform the analysis to determine how the actual value in forecast performance. So what we do is we determine the achievable advantage. We prepare some parameters and run our first proof of concept, which is a priced object. So our oracle, that the one that we built, it's rather simple, but it's quite informative. So we are creating an end-to-end solution. And what we are doing is actually comparing it with what about if we don't use quantum computing and we just do it with our supercomputer? And so when we compare the two, we find that indeed the scan concept it's much better. So it has 9.1 times fewer queries to determine what are the critical points. So it identifies really fast, 9 times faster than the supercomputer. And then, however, when we start to deal with the end-to-end auditing, that's where we actually our concept or ideas are not that good, because then we get into problems of loading from the classical to the quantum, and so the oracle cost is much larger. And so this indeed it's a demonstration that ideas could be brilliant, but in applications might not be that, and practical applications might not be that brilliant. So that's crashing with reality, which is good because now we can identify what are the pain points and try to address them in a different way. So we did additional budget, time budget on how this Oracle, how long it took. So to do this search over a synthetic globe, it took 6 seconds compared to the 2 microseconds with a CPU core, only one CPU core. So as you can see, we are way several orders of magnitude in this speed, in terms of speed. That's because of the limitations with the quantum memory, as many of you already know. So I'm just putting numbers and creating some ideas. Now, the question, and this one has been posed before in this workshop, is how to bypass this limitation, the QRAM. So I have been doing some research on what people have done, and Riken's Institute has introduced, or a long time ago, or maybe, or a few years ago, a methodology for not attempting to load the fields, but to only use it, the quantum computing for sampling. So we have to reframe our problem into a quantum sampling. And so that way we don't have to load the fields, not even the compact fields that we would like. So now we have that the other issues is that the system is chaotic, the search target is state dependent and non-recurrent. So that adds some issues in that we cannot actually use like training a lot, because for these time ranges that we're looking for, they do not repeat. It's a chaotic system. So we, in addition to this first proof of concept that we carried out, we are now preparing a reformulation. So we are going to do, instead of trying to find geographical locations where criticality is happening, we are going to create searchable objects as a cross-scale configuration hypothesis. So, for instance, in these cross-scale quantities or observables, we could have a convective transition pickup, microphysical advection, cloud size distribution, or whatever observations, instant observations are available, or model observations are available, and use those as our observables and quantities that could be resampled in our quantum computing. So in order to do that in a reasonable manner, we have to have also, in reality, a compact code. And then the question is whether this compact code, it's transmit that into the quantum computer properly, and then returns back and be useful for our decision making. So we created some null or adequacy to see, and started to do some, let's say, errors that we introduced to see if our system is actually doing the right thing or the results are from the right reason. So we have to train, or we have to tune our tools, our measurements that we are going to be using for validating our tests. Then in the trust number 3, it's about the I mentioned to you about the logistic error growth. This is important because then we are actually using a compact system provided only on these spanned by Lyapunov vectors, as I mentioned to you earlier. And for that, one could actually compute what is the forecast skill currency. And one of the things, well, we are on the middle of these experiments. It requires lots of computing and some sensors that we would like to use. So I'm actually opening here the sensing part. Data simulation, as you know, it's in between models and observations. But one that I heard in this workshop, it's the feasibility to learn to observe the storm state. And so this is something that I just grew from these discussions. So one could actually think about do a real data tier using these lightning jumps and create an anticipated product and see if this testing could work. So this is actually I'm not demonstrating this talk. This is actually something that I believe would be very helpful to test. So we would like then to collaborate with people to select lightning radio frequency bands for these circuit parameters and then tie that with our current experiments. So that could actually be something that it's kind of a plan for the future. Closing questions, and each should be gated. One is the representation. Can a state condition compact code satisfy decision equivalence faithful across flow regimes? The second is whether quantum front ends read the storm's electromagnetic broadcast with a measured margin over this geostationary LM and LMA class baseline, and then the value to show whether there is a value in amplitude estimation, and then determine that into probabilistic skills and hazard tails. So the motto of this is we compress the problem, not the bytes, and we are going to see whether sensing is or sensing the broadcast could help us in this problem. To contact you if you send me an email, because this is something that is really very important for this third part. Yeah.
Yeah, thanks a lot. Hi, good morning. This is Alex Guillaume from JPL. I think I saw on your presentation somewhere that your scheme depended on quantum random access memory, QRAM.
Yes. Mm-hmm.
And
yes.
I don't know if I'm up to date, but they are really more experimental than qubits, or in other words, I don't think they really exist. So how much does it depend on that?
Oh, yes. So first, quantum computing, and thank you for asking this question. The only thing I'm familiar with is what has been published in the literature, but probably if you could send me some more references on the QRAM new barriers or how they address that, that would be important, because for me in the proof of concepts, this is a wall. Loading data into the quantum, the qubits, it what took the longest.
I'll try my best. I'm not sure I'm a specialist on that, but I'll try to look for that.
Mm-hmm.
And on the point that Priyank had made previously, I've done some work on cloud size distribution, and we found power laws that were reminiscent of criticality in Ising systems. So I would also be interested in.
Yes, please email me. I think I have a white paper on using renormalization group theory for uplifting from the micro to the meso or high convective allowed resolutions. Yeah,
Okay, all right, thank you.
thank you.
Andrew Maciejunes, representing the Old Dominion University, and he'll be talking about hurricane intensification prediction.
Thank you so much for the kind introduction. So just really quickly, I would like to introduce the team to everybody. So among the four of us, we have expertise in quantum computing, predictive data analytics for public health and safety modeling and simulation, particle physics and machine learning specifically for particle physics. And we also have an expert in sea level rise and coastal flooding. Now I'd like to introduce you all to my home city of Norfolk, Virginia. So Norfolk, Virginia sits off of the eastern coast of Virginia. It is a port city. We are home to the largest naval base in the world, and we sit at a sea level of about 7 feet, or 7 feet above sea level. And we're also in a prime geographic location for plenty of hurricanes that come through the area every year. And because of those two things combined, we are prone to a lot of flooding, as you can see here in these pictures above. So as you can see, this chart right here shows you the amount of hours that Norfolk spends flooded each year over the past 100 or so years. And you can see an exponential growth in recent history. In 2024, we spent nearly 550 hours flooded, and I can save you some time. That math is about 23 days that we spent flooded just in 2024 alone. So it's very plausible that in the near future, we're going to see at least a month straight of flooding in a given calendar year. And so this graph right here, you can see the sea level rise of the Norfolk area over time and how this raises the threshold or lowers the threshold, but for the flooding from the minor, moderate, and major flooding, as the sea level rises, it takes less rain for us to see any sort of flooding. So in the past 2 decades, you can see at the right end of the graph, we've had a large concentration of storms that cause significant levels of flooding. And with this rise in sea level that we're seeing now that even weak storms that you wouldn't know by name are presenting a challenge to the city of Norfolk in the flooding that it's causing. So you can see Hurricane Erin right here from last year. You can see the path that it took on the right-hand side. It never actually made landfall with Norfolk or with any of the United States. The closest that it got to the city was about 150 kilometers. And you can see from the pictures here, we still experienced some significant flooding for about a day, with its peak reaching just at the 5.5 foot level. So our goal here is going to be to try and predict flooding before it happens based off of the features of the storm. And the reason for this is that we want to give the first responders and decision makers the appropriate or as much time as possible when it comes to the decisions they have to make regarding emergency evacuation and emergency planning. So this graphic that you see right here is the paths of different storms over the past 40 years and the path that they've taken up the East Coast with this black line in the middle. This is the average path that a storm takes, and these dashed black lines represent the standard deviation, with the yellow triangle representing Norfolk. So we're within one standard deviation of the mean hurricane and tropical storm that's going to come up the East Coast. And as I said a few slides ago, it doesn't even have to hit Norfolk directly for us to see significant flooding. So the majority of storms that go up the East Coast are going to impact our city one way or another when it comes to flooding. And so why do we define flooding at 0.6 meters? It's right in between the minor flood and the moderate flood level. And the reason that we define it right in between is the sea level rise. We wanted to compensate for that by essentially raising the minor flood level threshold relative to the sea level rising. And so our approach to tackle this problem is going to be a quantum augmented machine learning approach. It's just a 4-step process, with the first step being your normal typical pre-processing of your data. The second step is going to be classical and quantum features going into the machine learning models that we're going to use. The third step is just comparing our different models, the quantum augmented model and the classical model. We're going to do 3 different models: logistics, regression, gradient boosting, and neural networks. And then the fourth step is just the validation. So we use a 5-fold cross-validation split, 80-20 train test split. So what this means is we split our data 5 different ways, and we run the same tests on the 5 different training splits, essentially to make sure we didn't get lucky with the train test split that we chose. And so there are 3 different ways you can bring quantum computing and machine learning into our project. So the first way is the relatively simple tried and true method of classical machine learning that everyone's familiar with. You have your data, you run it on a classical computer and a classical model for training, and then you're going to deploy it in the same way that we're all familiar with. And then there is quantum feature engineering method that we use, which requires a quantum computer at training and at deployment. And then there's this third framework called LUCP, which stands for Learning Under Quantum Privileged Information. The cool thing about this LUCP framework is that it only requires the quantum computer for training, not for deployment. And under the proper conditions, it has improved efficiency and accuracy compared to a classical baseline model. So just to go over the classical machine learning model once more, it's just going to learn from your labeled data set, but importantly, this is going to just serve as our classical baseline to compare our quantum augmented model to. So the quantum augmented model is going to work by using a hybrid classical quantum data set. So we're going to take our classical data, we're going to run it on a parameterized quantum circuit, and then we're going to measure different observables, the expectation values of different observables, use these values as features on the data set. And so then we will have combined classical and quantum feature set. And then we're going to train a classical model off of this feature map, or off of this this hybrid feature map. And so then the third idea, LUCP, learning under quantum privileged information, it works very similar to the quantum augmented one, just with the feature engineering taking place just at training time. The idea is that it is able to learn the relationship between the data using the quantum advantage that you see during training, and then it doesn't need the quantum computer for deployment because it's already learned the relationship between the different data. So LUCP is it is provably better than your classical model under certain hardness guarantees or hardness conditions that we haven't been able to prove for our model yet. And so because of that, this is actually the next step for our project, and we haven't gotten any results for LUCP. So the following results are just going to be comparing the classical and the quantum augmented model from the previous 2 slides. So you won't see any results from LUCP today, unfortunately. And so just to talk about how we evaluated our model, we used the area under the ROC curve, which is the true positive versus the false positive rate. A value of 0.5 is equivalent to random guessing, whereas a value of 1.0 would be a perfect model that has 100% true positive rate. And you can see in the graph on the left, the red is going to be your classical baseline model, and the red is going to be your quantum augmented model with the quantum feature engineering. And you can see the quantum model does significantly better across all 3 of your models: logistics, regression, gradient boosting, and neural network. And then validation, we have the 5 different cross-fold validation splits that you see, and across the different validation splits, all the models performed relatively the same. So this means that we didn't get lucky in the training test split that we chose, but that the model actually seems to be learning from the quantum features that we're providing it. So what I would like to summarize is that Norfolk is a port city, and we are prone to a lot of flooding, and we're not the only port city out there. There are a bunch of them all over the East Coast that we can serve as a model for, that could potentially use the work that we're doing. And our overall goal is to save lives and or minimize the impact of hurricanes to everyday operations in Norfolk, Virginia. Thank you so much for the talk.
Thank you, Andrew. Any questions for Andrew?
That's great. Why? So can you elaborate a little bit on why this adding quantum computation in the system, neural network system, and improves accuracy and also time maybe, but accuracy, why?
So no, I can't tell you why. That's what we're trying to figure out. We just put the data into this quantum augmented. So yeah, we use this quantum augmented framework, and we observed on another problem, just when we were messing around with some other data, that it did better. We couldn't figure out why. So we tried it on a few other problems. We still couldn't figure out why, but it was consistently always doing significantly better on some other data sets. So we brought it to hurricanes, and we're still seeing the same thing. But yeah, I would love to figure out why.
Your presentation. I'm Hosel Bai from Vanderbilt University. I'm very interested in your basic model structure. Actually, maybe I'm missing a lot. I didn't know the spatial domain is how large it is, and then the variables you trained in your neural network is how many variables you trained, and then what neural network or the AI tools you've been trained. And so the differences between the quantum and the classical, and then also how long it takes to spin up this model and make it to the steady state. A lot of the nitty-gritty things I didn't really understand. That's why when it came to, his question is why it is better, and then I still having a confusion about, okay, the setup, the models or the different computers and.
Yeah, so I didn't implement the neural network. That was our machine learning colleague. So I can't speak to the parameters that he used or the hyperparameters they used for the neural network. The logistics regression and the gradient boosting were just imported from, I think, scikit-learn. So that was the model that we used. My portion was the quantum feature engineering. So what we did there was map the data to an ansatz, and then we used the classical shadows method, observing in different polybases, and then using those different measurements as the quantum features. So we're using the same classical feature set in addition to these quantum features as well. And then those are going into these different models.
So for the variables itself, it's very like, what can be a difference between when we come to the atmosphere, weather and climate, we often talk about tornadoes or this like extreme disastrous event is really closely connected to the floodings. And then what's the model structure would be the differences between this tornado system or thunderstorm system, mesoscale system versus the floodings?
You're asking how the models differ for different extreme weather conditions?
Right, yeah.
I'm not too sure. So we did do it on tornadoes a while ago before we did hurricanes. And we used a very similar approach, just feeding it into your normal gradient boosting and logistics regression. We also used just a pure quantum neural network with no quantum feature engineering. And we saw better results from the augmented data that has both the classical and the quantum features. As far as any other extreme weather events outside of tornadoes and hurricanes, we haven't looked into that, so I wouldn't know how to transfer to another model for that.
Ladies and gentlemen, nowadays, a day cannot pass without an extreme event reported somewhere. Something like tornadoes in mainland America and hurricane storms, classical computer and AI to better predict the extreme event. For example, if we want to save people's lives from tornadoes, we need the lead time to be longer. So currently, it's only about 15 minutes. So this workshop is timely, and also we have next generation researchers to be ready to take on this big task. Now I would like to invite my note taker and to do the presentation. And also I want to thank all the 20 people in our breakout session to contribute the ideas and suggestions. Thank you so much.
Hello, my name is Aziel Lumbo. I'm from California State University, Los Angeles. And I was a note taker, but I was asked to present this. So I'm very happy to fill in. And yeah, so we basically started with the first one, hybrid quantum classical workflows. We wanted to answer what are the most promising pathways for combining AI, HPC, and quantum computing to better understand and predict extreme weather events. And then we discussed, are there any opportunities where quantum computing complements rather than replaces traditional supercomputing? So first things first, got to identify critical points. Using hybrid systems for parameterization and optimization, such as in hurricanes, typhoons, and heat waves, and other extreme temperature events. So we also need a more understanding of physical events. It's not just the physics we're concerned about. We're concerned about an interdisciplinary call for here. So we really want more research in I feel like that'd be something we'll be saying even 50 years from now, more interdisciplinary research. So I've been a big advocate here at this whole event for atmospheric chemistry and quantum chemistry. So I kind of threw that on there. And global properties could be attainable with quantum computing rather than local properties in the Markov chain. We also need a specific event as a test bed, maybe precipitation event or extreme temperature events. We kind of identified that precipitation events might be a little harder to study, so maybe extreme temperature events would be easier. PINNs is not always suitable for quantum-informed neural networks and AI processes. So what I have highlighted is our kind of like our main points, and what I have not highlighted is kind of like a little bit of extra fluff. So there is a challenge in building accurate model run is not purely a result, and HPC has trouble with spatial resolutions, which will likely create a bigger initial condition problem. So next, we discuss the sustainability of use cases. Which specific weather events are most viable candidates for a near-term hybrid quantum classical implementation? What are the specific criteria that differentiate them? What current bottlenecks in extreme weather prediction are fundamentally computational, and which are scientific or observational? Where could quantum computing realistically make a difference? So remember how I talked about extreme temperature events over precipitation? There's also severe convective storms, including tornadoes and hail. And each of those follow different governing equations. So we're going to attack for those from all ends. So then we identified some bottlenecks. The biggest one, read in and read out challenge in solving nonlinear PDEs. So some solutions we talked about was develop a hardware or midware between classical and quantum computers to transfer data. Another solution was to formulate our clearance into something that can be easily taken by the quantum state. But even so, we haven't even achieved quantum advantage for linear PDEs. And I have it next on the slide. So another bottleneck, phase transitions is problem. The phase transition problem is difficult to be modeled, but nonetheless important for extreme weather events. There's also hope for quantum sensing for lightning observations, and Q2Q for NVIDIA may be used for GPU accelerated quantum acceleration if you don't have hardware access. So there's still hope that sensing observation may be important, and there really is a call for a common project between atmospheric and quantum computing. You know, there's always this focus on higher resolution, but remember as a slide before, it just might introduce a harder initial condition problem. So we also don't have the resources, and this is not even mentioning the non-linearity we've been going over. Tuning is inefficient and time consuming. Hopefully optimization may come into play, and joint schemes are just simply lacking. So then we talked about the infrastructure. What research infrastructure, testbeds, data sets, or collaborative activities would be most valuable for evaluating quantum computing for extreme weather? Examples could include field campaigns, laboratory testbeds, benchmark problems, community data sets, partnerships with laboratories, or shared facilities. For example, it was brought up NCAR has GDEX, and quantum researchers put their data on GitHub and papers published on arXiv. So basically, data exists. It's out there. Let's talk. And you know, as I said before, more interdisciplinary research is needed between math, computer science, electrical engineering, quantum mechanics, civil engineering. What also talks is money. We need for grants from various agencies such as NSF, DOE, DOD, and NASA. And you know, this is basically just fostering collaboration, which we're kind of already doing here. So identify the middle point to be quantum computing, HPC, and classical computing, which is always a goal for us. Lastly, we talked about benchmarks. What performance metrics or benchmarks should we adopt to objectively measure the advantage of quantum enhanced weather models over existing classical methods? So there is a want and hope by involving quantum computing AI that there will be extreme weather prediction to be faster, accurate, and more robust. So what we all want. For example, Tim Palmer yesterday said quantum chaos may be beneficial for ensemble analysis. So there's also a need to use smaller events to set up testbeds, such as severe convective storms and tornadoes. There's already a societal need for this. For example, as Grace has said, the tornado forecasting lead time is only around 15 minutes. I learned that today myself. So there is a need to run testing faster to give people more time for preparation for survival. And AI, we also discussed that AI models output is biased on input. And the answer to that is no theoretical proof exists can make things more accurate. So that's basically what we discussed in our breakout session. I thank you all and Grace specifically for giving me the opportunity to speak and present what we discussed. Thank you.
All right. So our group were given this task of thinking a high level rather than specific aspect. So we've been here for 3 days and thinking about different aspect of this marriage or collaboration. But so we're now stepping back, thinking about how we can sustain this or how we can build a better community. Right. So the task is to look at ecosystem, the combination of the quantum community and the climate or weather community together, right? So we're tasked to look at what do we have right now and what we're moving towards, and what we'd like to see, how we move toward. So for now, first of all, just so we had really enthusiastic community discussion. People were really provided a lot of input, and so what do we have now? This ecosystem. So basically, this is the people, right? And so the ecosystem is almost non-existent, almost not there. So, but we're building towards that. But the current effort is very much fragmented, right? So, and also can dive a little bit deep into that. So there's some aspect we discussed, like including we have trying to collaborate with the industry, but at the same time, we're also competing on the workforce, right? So they have the advantage of the finance, and but we also should recognize that we also have some advantage, that is the novelty of what we are doing. And as an oceanographer, we also sell to people. We're working on some really cool problems, right? So that's also a way to attract talents. So, but we also work together with the industry, and then thinking about the future, we also like to be systematically connected to the industry, or academia to industry, be systematically connected, and then together we can work together on the designing of the algorithms, or for either of climate or weather or related areas, and then also trying to bringing the climate or weather community, a lot of us, into this existing quantum funding initiative. So there are some examples from NSF or DOE, and also, at least in the near term or short, we should maybe focus on some bipartisan use cases that I will elaborate a little bit more. And then, and another aspect we would like to really we think the community should work on is the education, right? So education of both undergrad, graduate, but also professionals, that people like me that and I'd love to learn, and then bringing these opportunities to students. And then also we'd like to we think better to establish some structure for this kind of joint effort, in terms of maybe establish some institutes, and then provide some formal training opportunities like summer school or some tutorial opportunities. And then we would like to move forward, but it's also maybe be more effective. We can identify some champions that really to carry this forward, push this community forward. Next. All right, so to elaborate a little bit more on some of the aspects, like building the community, combining the quantum and the climate and weather communities together. Now, for the short term, maybe we can focus on using the existing modeling framework we have for the community, for the climate and weather, but identify some problems that we can use in the existing either existing or the hardware, near-term hardware. The hardware we can achieve in the near term, but so to optimize our climate or weather research. But at the same time, longer term, maybe we can think about maybe a new framework for the climate or weather research. And then, as I mentioned earlier, create structurized opportunities, including funding opportunities and the institutions, and then also should work together to identify some fundings and also work together on pursuing those opportunities. And I think we already mentioned the rest on this point, but then the next one, and to really strategize the connection or the ties between the industry and academia, including the government agencies and also other users. All co-designed applications, right? Really work together with the industry, and the industry with us, with academia, on algorithm and also the hardware. So that's something like we spent quite some time talking about the hardware and how the system could perpetuate itself, by working with the industry on the hardware. So if we are if the industry keep provide open access to the hardware, that will help us on designing applications. But at the same time, we will come up with new applications that will help them to design their hardware. So that's a self-perpetuating algorithm mechanism. And then so that mentioned open source, that and including open challenges, and also we can identify some open use cases. That one example Alex brought up is the example is NIH. So I'm actually was not aware of that, but there is apparently a NIH had a major effort on that, a grand challenge to identify to work on some CFD and partial differential equation problems for blood vessel flows, and to have some lessons or some experience that we can learn from, and as a community. And then besides that, besides industry, but there are also other quantum applications that are existing that are probably ahead of us, or have this community, like quantum finance or chemistry. So there are some lessons learned there, or there's some experience that we should learn from as well. So we probably should be connected with them on those fronts. And then, as I mentioned earlier, for the near term, probably it's better for us, maybe good, strategically good for us to identify some more societally relevant, directly relevant questions like flood, as we heard this morning, hazard, and also on particularly the weather events on local communities, right? So, and then we spent quite some time talking about workforce development, right? So to add a little bit more details into that, so talking about curriculum development, but we definitely need some sort of introductory curriculum for students and also for professionals like us. And then examples like quantum for climate for dummies, right? So that, and with some toy problems, people like me without background but has some knowledge in climate or oceanography applications can learn. And then also to for people from different communities to come together to co-advise students, right? To and also partner with the industries for funding and education opportunities. So see what kind of workforce they would like us to train, and how we can help them on the same time, as I mentioned earlier, help them on the design of their hardware or software, right? So that's all we have. I thank Malo and Swamit on working on this together. Yeah.
Thank you so much. So before we head into concluding remarks and kind of overview of the workshop, we just wanted to open up the room for really any final thoughts, discussion. We have some time, so this can be on any topic that we discussed. So if anybody has any questions or comments they'd like to make, now's a good time to do that.
Ruben, thank you so much for organizing this. I just want to ask, so looks like everybody here is very passionate about contributing to this. So after this event, this meeting here, is there a way we can help, for example, to do some report? Can we do something for the reporting?
Yeah, we definitely do want help. I don't think we've discussed exactly how we're going to ask for feedback from all of the participants, but I know that we do want your help. I guess just brainstorming off of the top of my head, you could send, or we could have a directory somewhere where people just kind of put all of the ideas that they have kind of in a succinct format. I don't know if that's the best way to do it. So maybe I'll just say yes again, and maybe wait for further guidance so we can discuss exactly how we want that. But absolutely, we want everybody's opinions and voices to be in this document as much as possible. Thank you for the question. I guess kind of following on that, you mentioned connecting, I think, also, or staying in contact. Swamit, you did have a few comments on that. Now might be a good time to make that.
So I think this point was brought up again and again, that how we all can stay connected. So Slack channel is one option. We could also start a mailing list. Happy to, take the lead on that, on those two ideas. Again, if you have any other feedback regarding this, please come talk to me, and then eventually we'll figure out how to stay connected. Yeah. And then I think there was another sort of, thought about creating a website, putting all our materials there. We can also do that. It's not a very, it's a low overhead thing. We can do that.
Yeah, I think like as an institution, NCAR, has a lot of programs for graduate students, undergraduate students, and visitors. So I think like this would be like a very good idea to stay connected. So during this summer, if you have a student who wants to work on specific modeling related stuff, you can come here. We have a lot of funding from National Science Foundation on that area. So I think don't think of us just as model developers or model builders, but we can jointly participate in the training and workforce development area. Yeah.
We have a comment online from Charles. A recurring theme today has been separating computational bottlenecks from scientific and observational ones. For a near-term hybrid quantum classical testbed, how should local discrepancy data, where forecast sensors and actual conditions disagree, be structured so researchers can identify which bottlenecks cause the error and determine whether quantum methods actually add value?
That's a great question. I don't have an answer, so I'll just say anybody who wants to provide any comments on that, please feel free.
So I just want to add on this question. I think this is really one of the greatest questions because one thing that we really want to figure out is like, even like classically, right? What are the grand challenges that we are facing in addition to this curse of the dimensionality in terms of the energy cascade of turbulence? So that is a very well established question that we can pose to the quantum computing colleagues to help us. But the other ones, for example, that we never really had any access to the quantum native phenomena of the atmospheric chemistry. Those ones are sort of those questions that it's more like a scientific question that we could answer using the quantum computers. But I believe there are a lot of other questions in terms of cloud microphysics, like the collision correlations. We don't even know how to describe the collision efficiency mathematically based on the physics, right? So those problems are like, you can't really answer those by just solving an equation. Therefore, the quantum algorithm colleagues, they also have no idea how to help you. So if we could come up with a more like a unified mathematical description of this like phenomena across scales from cloud microphysics all the way to general circulation, such that we have classically we are confident enough, okay, this is like a physics-based model, and then we need like a quantum speed up or some kind of quantum usefulness from the quantum computing community. Because if they don't know the physics, no magic would happen, right? Garbage in, garbage out concept.
Yes, I have a question following on that. If we have a fluid dynamics model with sufficiently fine spatial resolution, do we need to doesn't that sort of account for these processes that you're describing? Won't they be explicitly resolved rather than, some type of approximation that we use today? Or do you need to actually add on somehow, have other sets of equations that you're solving for as well?
I can maybe like add some comment on that. It doesn't matter. You are doing LES, still your turbulence is not resolved. You are doing DNS, still it is not resolved. So processes like turbulence, it is very tricky.
That maybe my understanding then is I don't have the right understanding of DNS. I thought the whole point of that is you don't need a closure scheme for turbulence. It is explicitly resolved. Am I misunderstanding something there?
Like, yes, you can do DNS for a very small domain. Can you do that on a global scale?
But can I add something on that? But that is the sort of the killer app for quantum computers, right? Because you look at the quantum query or gate complexity that the runtime scales or the circular depth scales as logarithmic of the number of grid points, right? So basically, I think your suggestion is great because that's the regime where we show that, okay, if you have like an efficient quantum algorithm to solve the dynamical core, you resolve all the way to the tomograph length scale. Basically, that could get rid of the closure models that you use in the global LES or those kinds of things. But in terms of the cloud macrophysics, you would add another layer, like how the particle and the field interacts with each other. For example, the latent heat release because of the phase change. But that would depends on the individual particles that interact with your thermodynamics fields and the turbulence. So the killer app would be, okay, if you want to resolve all of those huge number of the particles, as well as the turbulence all the way to tomograph length scale, and how can the quantum computing achieve this?
Yeah, thank you for adding that point.
Yeah, I want to also chip on that, pile on it, sorry. I think for quantum computing, we have to think differently. If we want to succeed, we don't have to think on trying to mimic classical approaches using quantum computing because we are going to lose. I mean, that's not how I think we should progress. We have to approach it in a different way. For instance, as you mentioned, we could run as high resolution as possible, but something that you cannot do with classical computers is when you have phase transitions. When you have from laminar to turbulent changes or phase regimes, it involves not only one microscale, but all the scales sometimes together. So those criticalities which were mentioned in the discussion this morning are harder to attack. And if my suggestion is not to attack them as a fluid or as a continuous field, but more like a quantized event, like rare events or critical events that involves multi-scales. And that's where I think the quantum computing will actually be superior than classical computers. So I don't expect in the future any interest on running a global model, not even an LES model, into a quantum computer. The quantum computer is best at something else, not on running those models.
Thank you for sharing. Are there any follow-ups to that or any other comments that anyone would like to make? Okay, if not, we can go into our concluding remarks. Okay, so I'll just start by saying thank you all so much. This has been a busy 3 days, but very stimulating discussions, and I've learned really a lot because we're bringing together so many different fields, which is exactly the point. So just a reminder of the workshop objectives that I shared on Monday. So first was to showcase what quantum technologies can achieve today. I think we did that with our presentations, our posters, also just through all of our discussions. So I think that was a big check. And, you know, a lot of those details will go into our report. Also, some of the questions that naturally arise when we're talking about what we can do today, but what we can't do today. The second point was an increase in collaboration. Again, I think we did this in spades. So we wanted to increase collaboration between quantum weather, climate scientists, and mathematicians to develop new research projects. I personally had a lot of discussions with various people in different fields on possible research directions. So personally, I know that this is a big check, and I was just sort of listening in on other discussions, and it seemed like others did as well. So I think we definitely accomplished this. The third point was to predict how quantum technologies will be used for weather and climate applications in the coming years as the technology and hardware matures. This is a hard one because you kind of need to take a risk a little bit when you're making a prediction like that, and you need to be a little bit bold. And we don't have that much information, to be honest, at the moment. I mean, we have some quantum algorithms, but we don't exactly know what they can do. So this is something that I think we did a little bit and just in some of this discussion right now, but we probably could have done a little bit more. So what I'll say is if others have predictions that you'd like to include in this report, we can include those. Okay, so overall, pretty good, I think. continue. So what were some of the high-level workshop observations that we made? First was a fragmentation of effort. Current research initiatives are largely operating in silos, with teams often totally unaware of how their findings could benefit or complement the work of others in the field. Missed synergies. There is significant untapped potential for cross-pollination between quantum computing, quantum sensing, and climate science that could accelerate progress in weather forecasting and climate modeling. Third, a need for integration. A formal collaborative framework is required to bridge the gap between quantum scientists and climate weather experts, ensuring that research is aligned with practical domain needs. And fourth, a strategic roadmap, increased dialogue to define clear technical requirements and establish a unified long-term vision. This coordination is to enhance impact without limiting the autonomy of research groups to pursue independent, high-risk, high-reward studies, leading to unexpected breakthroughs. So we actually have some specific recommendations that we wrote down. I think we probably will have more than this, but I think a few really key points came from certain discussions. So the first is, I think this question has come up a few times, which is what can the climate and weather community do today? And I think one thing that we can basically tackle immediately is that climate and weather scientists can write a review paper which identifies weather and climate problems that are tractable on near-term hardware, starting with foundational toy models. So that could be something like Lorentz 63 equations, and ultimately scaling up in complexity. Sort of one way to think about it is it could sort of be a letter to the quantum computing community for us to concisely outline the types of problems that we want to solve. So this came up in the differential equations breakout session, where basically we were saying we could have a paper where each section is sort of a very concise overview of very specific differential equations that we solve within weather and climate modeling. But I could imagine the exact same thing for other types of equations, just linear systems of equations, which I know show up in data assimilation or optimization problems. But basically, here are the types of problems in a concise manner that we would like to solve. And hopefully those in the quantum computing community could give us an idea of which of those may have the possibility for some type of advantage, which are just known to always be impossible for very specific reasons. So I really like that recommendation. Next would be quantum computing introductory talks should be given at existing climate and weather conferences like AMS and AGU annual meetings to help non-quantum computing researchers get involved. So this is, I think, pretty low-hanging fruit. Something we've identified is people in climate and weather are interested in this, don't know how to get started, and just sort of this would help make it easier for them to sort of take those first steps. We could even consider a standardized presentation to make it easier for the presenters so that we don't have to reinvent the wheel every time we want to give an introductory talk. And that could be freely available to anyone who wants to give these talks. If you're going to, one of the big meetings or even a smaller one and want to give an overview talk, it could be something, it would make it a lot easier for you to get started and to do that. The next recommendation would be to expand opportunities for interdisciplinary dialogue modeled after this workshop. So crucially, fund and organize joint summer schools and tutorials for early career researchers to build cross-domain expertise. This, again, is sort of part of the workforce development, but also just creating that bridge between climate and weather folks and quantum computing folks so that we can really work together. Some more recommendations, simply to define standardized metrics and quantitative measures across quantum and Earth system science and actively incentivize the community to publish core benchmark papers. Next would be to establish a working group so we could explore opportunities in US CLIVAR and other organizations to fund. So this could help push the field forward. And actually sort of part of this, it's already been suggested, but to help attract funding, it may be useful to create a website which is composed of organizations represented here who want to continue participating, but also maybe even other organizations that were not able to participate in this workshop. And there we could outline sort of our mission, which broadly speaking is bridging the gap between the weather and climate and quantum communities. And I would say something like this would show that there's a strong group of people who want to come together, and I think that could enable future funding opportunities for recurring meetings. So these are just some of the specific recommendations that I think will come out of this, and they'll be refined, and I think we'll add many to this. But the last point I'd like to make on the recommendations is we would like to look for a lead to take each of these and others further. So please let us know if you're interested and want to volunteer for any of these or any other recommendations you have in mind. That way, they're not just kind of buried within our summary paper. We actually do something actionable with them. So something to think about. So some next steps after the workshop. Of course, we want to submit a journal publication, which is meant or geared towards a broad audience. So it could be something like BAMS, and we want to do that by the end of this year. And once again, those will include major workshop themes, new developments within the various fields, list of near-term applications, key discussions that were had, consensus and/or differing views that were reached, and the recommendations that were made. And then we will be giving a briefing to US CLIVAR interagency group, which is comprised of ONR, NASA, NSF, NOAA, and the DOE program managers. And I think we should really look at this as an opportunity to attract more funding for other workshops like this. So if we have something like a website which shows that there's a strong group behind this, maybe other actionable items that we're actually doing, that may attract more funding for the future. And we definitely want to advertise to these people that there is interest in continuing workshops just like this. So we are going to move on to a survey. So actually, now we'd ask all of you to take out your phones or computers and scan this QR code, and you'll be asked some questions to fill out. So I'll give you a moment to do that. Has everyone scanned this code?
All right. So we prepared about 5 questions for you, and I put a 3-minute timer on each of them, so it shouldn't take longer than 15 minutes for all of this. So the first question that we like to ask is, what was the most valuable part of the workshop for you personally? So that can be anything that you participated in, either here or in the evenings or anytime. Just note also that you should be able to see the answers of other people as they appear, so you can like them. So you don't have necessarily to rewrite what others have said. You can just like them if those are the ones that are also true for you. All right, it seems that a lot of answers are about networking, so I'm glad that everybody's enjoying the in-person meeting. I wish I could be there with you. We've got about a minute left. See that answers are slowing down. Some more likes. All right, 20 seconds left to look at the answers and like the ones that you prefer. Then we'll move on to the next one. Okay. All right, second question. So what should we include in a future workshop that you think is really necessary? It can be something that was already part of this workshop or something completely new. All right, lots of people wanting tutorial sessions, I see. All right, 1 minute left. All right, 5 seconds, and then we'll move on to the third question. Lots of answers, thank you very much. That's great. All right. Okay, let's move on to the next one. I'm not sure. Okay, so what could be improved about our workshop and how? Thank you for that feedback. I see some suggestions that also fit with the tutorials, so that makes sense. Got a bit more than 30 seconds left if you want to like the answers that you prefer. Moving on to the last question in about 5 seconds. All right, thank you very much. And now for the last one, going from the discussion that we've just had, so how do you think that we should keep the momentum going from this meeting? Already some suggestions from comments at the end, but let's see what you can come up with. I think it's great that many of you want to meet another time very soon, so that's great.
Someone even said next month.
Yes, exactly.
That's right. We'll try to throw it together.
Yeah, many people also recommend making it an annual series, so yeah, let's try to make that happen. Some suggestions about working groups also of different sizes, Slack or other channels. All right, we've got about 20 seconds left, so like the answers you prefer, and then the survey will be over. All right, so that's it for me and the survey.
Thank you, Carl. So will we see these responses? Will we have them available to us at some point?
Yes, of course. I can already share them.
Okay, cool. Yeah, it'll be nice to read through each of them. Okay, with that, we're going to get into the final remarks as soon as I can advance. Yep, there we go. Okay, this one is just a reminder that if you're interested in the tour at Elevate Quantum, but this will be a designated tech hub by the Department of Commerce, Economic Development Administration. It's a regional consortium of 120 organizations, and the mission is to dramatically accelerate the pace of commercialization in quantum. I'm really excited. I don't know what to expect, to be honest, and I'm looking forward to it.
Yeah, let me give a short intro. Elevate Quantum is the consortium in Colorado, New Mexico, and Wyoming, spanning around 120 plus organizations, including universities, industry, etc., all focused on quantum. And while there is the consortium part and everything going on at the individual organizations, what will really power these organizations is research infrastructure, test beds. And that is what happens at the Quantum Commons that we're going to visit this afternoon. The Quantum Commons has existed for like 1 year, and that was when the 70-acre land was made available, new buildings, and now more and more research infrastructure has moved into these buildings. One is a quantum computer, a superconducting quantum processor in a dilution refrigerator. There are also facilities for environmental testing of quantum sensors. There is an atomic clock available there where other university groups, but also startups can come to benchmark their equipment. So it's really a facility for shared use, community use, early startups that don't have the funding, universities from the region, but also beyond, and lots of opportunities for collaboration. There are similar initiatives in multiple spots in the country. Yeah, we have representatives here of the Illinois Quantum, and Microelectronics Park. Hope I phrase it correctly. There are initiatives going on the East Coast, but would love to show this collaboration model here locally and build collaborations.
Thank you, Marlo. Okay, so let's thank our sponsors, Office of Naval Research, for allowing this opportunity to take place. So we can give them a round of applause. And another big thank you to, I'll say personally, to the entire scientific organizing committee, my co-chair, Anna Rita, who's done so much, and it's been amazing to work with her. Marlu, Anish, Swamit, Felix, and Carl, the same. It's been really a pleasure to work with each of you, and I've learned a lot about various things from you, so thank you for your help. And the program organizing committee, we could not have done this without them. There's so many little details that go into planning something like this. So Alyssa, thank you so much. You're amazing help. And yeah, really, the entire reason this is running smoothly, I think, is largely due to Alyssa and Mike, who has recently retired, but has provided a tremendous amount of help, and Jessica and Rebecca as well, both from UCAR. And thank you to all of our panelists, Joyce, Caroline, Jason, and Whale, all of our speakers in person and virtual, and our breakout session volunteers, Husail, Maribeth, Aman, Rubayat, James, Sahara, Priyant, Kanth, Abinaya, Carlos, Andrew, Grace, Aziel, and Wei Feng. Thank you all so much. This is really a collaborative effort, and we appreciate you signing up and volunteering your time. And finally, to our UCAR multimedia team, Kelvin and Chris, who basically everything has gone completely smoothly because of them. It's been amazing. So I like this facility a lot. Let's give them a round of applause. And also everyone for attending and your lively discussions. This is more than just people coming on stage talking about their research. This is about other people sharing their opinions and having conversations. And I think we had very lively discussions that it's been a pleasure to be a part of. So thank you for everybody. So I'll just give some small concluding remarks over the picture we have here, which we can share. So as we close this workshop, thank you all for the 3 days of thoughtful discussion, new connections, and meaningful collaboration. While it is clear that quantum technology is not a magic solution, we've explored some of its potential and also some of the challenges that we face that we need to solve. I hope this workshop has laid a strong foundation for future pilot studies. And beyond the science, I'm really glad that we started building this community. My hope is that we keep these connections going, bridge the gap between fields, and stay in touch, hopefully with future meetings and just individual connections. So again, I'll just say my sincere thanks to our speakers, presenters, breakout leaders, poster contributors, and all participants, everyone who asked a question, made a comment, everything, both here in Boulder and in person. And thank you all so much. So I wish you safe travel. And for those of you going to Elevate Quantum, I look forward to enjoying a few more hours with you. So thank you, everyone.